There we have it, right? So let's plug this in. Velocity is the square root of 6.67 e minus 11 times 5.97 e24 divided by this guy here, right? 6782250 meters. I don't need to square that, right? 678. Did I get it right? Is that right? It somehow seems wrong, but it's correct. Yes. Take your calculator and calculate that. Every man, woman, and child. Is this a close orbit or a far orbit, relatively speaking? Do you guys get 7662? And we only have basically 2 sig figs. So you'd have to say 7,700 meters per second is about. Right? This is what we think it is, but there it is, right? About 7,700 meters per second. Is that fast? Yeah, it's kind of fast. I'm going to convert to miles per hour. So times 2.237. That's 17,000 miles per hour. Yes? The fine for doing that in the school zone in front of the school is 327,600,000. I just made it. I really don't know what that is. Yeah. So 17,000 miles per hour, 250 miles above the Earth. If this is 4,000 miles, right, then this is 1/16 of that distance, right? So basically the space station is how far from the surface? It's like right there. It's a 1/16 of that radius above it. So what does the Earth look like from that distance? Well, it's kind of cool. It looks like this. I mean, if you put your head up this close to a globe, you can see that it's round, but it takes up almost half of what you can see, yeah? Yeah? It's like, there we go. Okay. What's the other orbit that's important to us?
The ellipse.
The ellipse. The other satellite orbit, artificial satellites, almost all of them orbit at this distance. What is that distance? Do we know? How many people have a satellite dish on their house? Yes. Does the satellites move? Does the satellite dish sit there and track across the sky? Nip, 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 nip. Or does it just point to one spot in the sky? How does it do that? It points to one spot in the sky. How does it do that? Is it possible that the satellite is in a geostationary orbit? That is, it is in orbit, but it's in a point out here where what? It stays at the same spot overhead. The only way it does that is that it's going around the Earth the way the Earth is turning at the same, not the same speed, but the same period of rotation, right? Okay? Yeah, that's called the geostationary orbit. If you look at a map of all the satellites around the Earth, there's this enormous cluster of them right on the geostationary orbit. And then there's a whole bunch that are either too far out or too far in. What are those guys? Are those the dead satellites that they've just sort of nudged out of the way? Yeah, it's packed, especially over like North America. That real estate, okay, is actually, they track it. Everybody's got an assigned place to be in the geostationary orbit. They don't want people being too close to each other, right? Okay, so yeah, that's kind of an interesting thing, right? How far away is geostationary? Anybody know? It's not real close. It's not real close because you actually need a dish, a parabolic reflecting dish to catch the signal from those things, right? So that's the next thing. Let's calculate the radius of a geostationary orbit. Okay. Before we move away from this orbital speed, understand that is really fast, right? So if you encounter a piece of space junk at 17,000 miles per hour, what does it do to you? We think it would go through your spacesuit, right? So they take it pretty seriously. If they've got shuttle astronauts and stuff exposed to space, it's probably going to go through the walls of the space station, right? So this is one of the hazards. You know, if you lose a wrench in orbit, okay, that wrench at 17,000 miles per hour would hurt more than a bumblebee, right? When you're riding a motorcycle, right? Bumblebees hurt, right? You know. a wrench going 17,000 miles per hour is like Armageddon, right? Okay, so that's why when Ronald Reagan was doing this whole Star Wars thing, and we're going to make these things that'll shoot down missiles, and we're going to put billions of dollars of satellites up in orbit that will shoot down missiles. All the scientists knew that it was hooey, that it was hooey, right? It was just they're trying to put the Soviets out of business, and it worked, by the way. Okay, it's hooey because if you make a multi-billion-dollar satellite system to shoot down my missiles, okay, I'm going to defeat it this way. I'm going to go to Home Depot. I'm going to buy a bag of pea gravel. I'm going to put explosives in the middle of the bag of pea gravel, and I'll put it in an opposite orbit to your satellites. Yeah? And whenever I want them to be gone, I explode that pea gravel, right, into a big space, and one of those little fragments is going to strike your satellites, and it's not going to be going 17,000 miles per hour when it hits it. It'll be going 34,000 miles per hour, right? And it's going to burn, freaking little holes all the way through everything, right? They actually did something, and NASA put this satellite out just to see what exposure to space did, right? And they found that these things that just sat out there for a long, long time, they looked at it, and they're like little miniature craters, like the craters of the moon, where solar system dust came in and just smacked into the walls and made like little burn marks in it, right? Yeah, wear your helmet.
Okay, so
yeah.
Why does it look like when they accidentally go with a wrench, it just looks like it's floating? Why not?
Yeah, because everything is moving 17. The question is, why doesn't it look like it's going so fast? Because everything, the mass, the orbit does not depend on the mass, right? So when the wrench separates from you, it's moving with you at 17,000 miles per hour, right? But somebody else in some different orbit might encounter it at a different velocity. Right, and that's what keeps it from falling right down to the earth, right? Is that you've got this, if you put yourself in that frame of reference and use the F word, right? Gravity's pulling you in, centrifugal force flings you out. So orbit is the equilibrium between that, and that kind of works, doesn't it? It's off, and next time I see you, I'll use the F word a lot to explain how gravities work, how orbits work. Let's solve for the orbit, geostationary orbit, and then let's see if we can get you guys to do. Let's see if we can get you guys to solve one of these problems. Okay. So geostationary orbit, right? And it's stationary with an A. The one with an E is you write on it. It's like paper, right? Okay. The period is, well, what is the period of a geostationary orbit? That's like that's like around the sun.
Okay.
For people living on the sun. Like 24 hours, is it?
23.
Yeah, actually, yeah, what is it? It's 23 hours, 56 minutes, 4 seconds. Do we know why it's not 24? Do we know why it's not? Because of leap year. No? Okay, here's the deal. Did you think that the Earth spun in 24 hours? What is 24 hours? It's 24 hours from noon to noon, yes? And for sure, noon to noon is 24 hours, give or take milliseconds, okay? When there are clouds way out, a lot of clouds, water is, in other words, water removed from the surface of the Earth slows down, just like in IBI Park. When you pull yourself away from the center of that rotation, you slow down, right? And when there's not very many clouds, the Earth speeds up a little bit, yeah? Okay? And so there are minor fluctuations. Every now and then they add a second. But why is the rotational period of the Earth 23 hours, 56 minutes, 4 seconds? Yeah?
Because when the Earth rotates, high noon will change based on where the sun is.
When the Earth rotates, high noon will change based on where the sun is. That's amazing. How do you know that?
Astronomy last year.
That's amazing. I have to congratulate Mr. Youngberg. Maybe we should blow him up with a firecracker. Okay, okay, here is, Juliana is going to be the sun. Okay? She is going to be the sun. It's always, by the way, the person who sits in that chair. Okay? So I am merely the Earth. Okay? And when she is right there, overhead, it is high noon, yes?
Yes.
Now, that would be dangerous. The question was, can I be the moon? And we better not do that, right? Okay, so there we go. Now I'm in the picture. Okay, so here I am, and it's high noon, and she's directly overhead. Now I'm going to do two things. I'm going to revolve around her, okay? And I'm also going to rotate on my own axis. Are we ready for this? Here is high noon. Okay, by the way, the Earth rotates in the same direction as it revolves.